Hello, dear students. Once again, I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Dear friends, this is my second video on IIR filter design numerical. Last time we have seen the numerical on the IIR filter design that we have already seen. So we have seen this problem of the IIR filter design, analog filter design. HA of S is equal to S plus 0.1 upon S plus 0.1 whole square plus 16. That we have seen the problem how this analog filter is designed into digital IIR filter. This also we have seen how we calculate the H of Z, and now we will go through this problem. This is a very simple and a very small type of design problem. It is required to design a digital filter with a 7 dB bandwidth of 0.25 pi from this 8 ohm analog filter having the following system response. This is the response, analog filter response is given here. HA of S is equal to omega C upon S plus omega C, where omega C is the center frequency of the analog filter, and using bilinear transformation obtain H of Z. So this function is given to you, and here this an analog filter having the following system response and 7 dB bandwidth with 0.25 it is given. So you can use BLT formula here. Omega C is equal to 2 by T tan omega R by 2. So here you can use, it is given in the problem 7 dB bandwidth. So you can use here 2 by 7 tan 0.125 pi. Then you can see H of Z is equal to H of S at S is equal to 2 into Z minus 1 upon T into Z plus 1. This is the transformation using using bilinear transformation. This is the substitute for S is equal to in terms of Z. So you can put here omega C upon 2 by T, Z minus 1 upon Z plus 1 plus this omega C is our given transformation. We here put this omega C is equal to 0.828 by T, 2 by T, and this is 0.282 by 28 by T. You can calculate this value like this. TT will be cancelled here, and we will get this H of Z is equal to 1 plus Z inverse upon 3.414 minus 1.414 Z inverse. This is the required transformation in digital filter, IIR filter. Now this is one more problem. Make the use of bilinear transformation to obtain H of Z if it is given that HA of S, you can see here, this HA of S is equal to 1 upon S plus 1 whole square and T is equal to 0.1 S. These two analog transfer function is given here, and the sampling time is also given 0.1 second. You have to use the bilinear transformation, that is BLT method. So we will put the transformation H of Z is equal to HA of S analog filter transfer function at S is equal to Z upon Z minus 1 Z into Z minus 1 upon T into Z minus 1, 2 by T into z minus 1 upon z plus 1. This is the actual transformation in place of s while converting from s to z. So this is the given transfer function. This given 1 upon s plus 1 square. So in place of s you can put this transformation. So 1 upon 2 by t z minus 1 upon z plus 1 whole square. You can simplify this, and simplified equation is z plus 1 whole square upon this 21z minus 19 whole square. And finally this h of z we can get this transfer function. So it is just simply you can put t is equal to 0.1 and s is equal to 2 by t z minus 1 upon z plus 1. This is transformation for BLT. Now this is important. One more problem is here. You can observe this problem. An analog filter has the following transfer function. HA of S is equal to 1 upon S plus 1. Using this bilinear transformation technique, determine the transfer function of digital filter H of Z and also write the difference equation of digital filter. You have in this problem one more thing is added. You have to write the differential equation for this digital filter. So from the digital filter transfer function we can go for the digital differential equation, that is in terms of x of n and y of n. So this is HA of S is equal to 1 upon S plus 1, it is given, and the bilinear transformation is S is equal to 2 by t into z minus 1 upon z plus 1. So you can put this value in the given transfer function 1 upon S plus 1. In place of this S you can put this one, and you will get here this transfer function. And later on the value of t here, value of t is also given in the problem. It is t can be assumed, t is sampling, where t is not given in the example. We can assume t is equal to 1 second. Here it is written, hence the value of t is assumed to be a 1 second. So you can put t is equal to 1 and get this transfer function. Later on, after getting this transfer function, you can write this transfer function as y of z upon x of z. This is z plus 1 upon a z minus 1. So you can convert this and put the equation by cross multiplying this left side y of z terms and right side x of z terms, and taking inverse Laplace, that is inverse z transform IZT of both sides. So you will find here a into y of n minus y of n minus 1. Z inverse means x of yz of z inverse y of z means y of n minus 1, and xz is y of n. Z inverse x of z, the inverse of it is x of n minus 1. So you can write this y of n is equal to 1 by 3 x of n, 1 by 3 x of n minus 1 plus 1 by 3 y of n minus 1. This is the required difference equation of the given problem. So any transfer function can be converted into the difference equation just by making the ratio y of z upon x of z and taking its inverse z transform, and one side is a y of z and another side, right side, is a x of z. You can take the inverse z transform and make y of n is equal to whatever is the equation, like this. Z inverse indicates the x of n minus 1 and x of z gives the x of n. So this type of numerical may be asked in the examination also. Again, one more numerical we will go for this IIR filter design in the next video. You can refer the standard book for these numericals. I am also having 1 or 2 numericals over here, so that we will see in the next video. These are the numericals. Thank you very much for attending and your sincere and listening this numerical solution. Next time we will see a better numericals on the impulse invariance technique also, and then we will go for the next numericals. Thank you very much. Thanks.